Hello. Hi. Hi. I feel like I'm getting a suntan. Hi, I'm Ashley. I'm the Director of Marketing and Communications. Welcome to our first Science on Screen event of the season. Very exciting. Yeah. Absolutely. So, before I started working here, I didn't entirely know what Science on Screen was, so in case anybody else is new to it, I'm going to give you a quick rundown. It's part of a nationwide network of independent theaters bringing together cinema and science for a unique blend of learning and entertainment. Science on Screen series features creative pairings of current, classic, cult, and documentary films with engaging discussions by notable figures from the world of science, technology, and medicine. With our partners at the White Mountain Science, is it White Mountain Science Inc.? Yes. The Science on Screen series at the Colonial is sponsored by Douglas Arian, Marion Secker, and Mountains of Stars. And it's an initiative of the Coolidge Corner Theater with major support from the Alfred P. Sloan Foundation. I got through my notes. Okay, so just letting you know, we are recording, hence the camera and the sun next to me. And that's just part of the Science on Screen event. But without further ado, I'd like to introduce Mike Carmon. He's the Summit Weather Operations Manager at the Mount Washington Observatory. Please give him a hand.
Thank you so much. All right, let me find my mouse here. Good evening, everyone. Again, my name is Mike Carmon. I'm the Summit Weather Operations Manager for the Mount Washington Observatory. It's great to be here this summer evening. So this is sort of an overview of what I'm going to be talking about before we roll the film in a few minutes here. So I'll start just by giving you a little bit more of a background for those of you that don't know about the observatory, its mission, and the work that we do. Then I'll kind of dive into some climate-related research that's going on at the observatory, two notable projects in particular. But then I'm going to spend sort of the bulk of the back half of the presentation just talking, kind of zooming out and talking a little bit more broadly about weather and climate and really science communication in general and sort of how that ties in to the film you're about to see. So first, a little bit about me. That's probably the largest my face has ever been on a screen. But a little bit about me. So I am a degree meteorologist and a maybe self-professed science communicator. I spent almost 10 years as a weather observer, meteorologist, shift leader, education specialist with the observatory. I left the observatory back in 2018 after spending almost 10 years living on top of a mountain and came to WMSI for about 6 years, kind of explore that education track a little bit more. But then an opportunity presented itself last year to return to the observatory in a position that was based out of our Valley office. And now I manage the team of observers that work and live on top of Mount Washington. So the mission of the observatory is to advance the understanding of the natural systems that create Earth's weather and climate. And we accomplish this mission through kind of 4 different areas of focus. One, of course, is our mountaintop weather station. That's sort of our claim to fame on top of Mount Washington. Since 1932, we're taking manual round-the-clock weather observations 24/7. In addition to our weather observations, we're also doing higher summits forecasting, which is used by many people. You all may have used it yourselves in order to keep the recreating as safe as possible and inform folks to hopefully make good decisions when they're in the backcountry. But that's just one part of what we do. We also have a growing science education wing of the observatory as well, sort of inspiring the next generation of scientists. And we do a considerable amount of research, having this very long-standing data set going back to the 1930s. So we do a lot of cutting-edge weather and climate research. We have a thriving internship program. We have dedicated research observers that work on each shift. And then we do some cross-organizational collaborative projects as well, which I'll talk a little bit about some of those too. And then finally, we are an historic organization, having been around since 1932, so we've sort of taken it upon ourselves to interpret the heritage of the White Mountain region as part of our mission as well. So getting back to sort of that weather and climate research side of things, so I'm going to talk about two different projects here relating to climate research. One that is completed and one that is almost going to be complete, or is almost completed, that will have a public-facing product that will be released to the public, hopefully in a few months here. So something to look forward to there. But before I dive in, because we are going to talk a little science, there's going to be some charts and some tables, but just for a couple minutes. So just some things to keep an eye out for before I dive into those things. Keep an eye out for units. I'm going to be talking between degrees Fahrenheit and degrees Celsius. I'll try and warn you when I switch between the two, so keep an eye out for that. Also, I'm going to be talking across some timescales as well, since we're talking generally climate research. Climate generally means we're talking over long periods of time. So we're going to be talking in terms of years and decades with a lot of the numbers I'm going to show you. And then also locations, especially for the next, or the first project I'm going to be talking about. We're going to be looking at data sets from the top of Mount Washington at 6,288 feet. And we're also going to be looking at a data set a little bit closer to the ground at Pinkham Notch Visitor Center at about 2,000 feet. I'm also going to be throwing the term significance around quite a bit, so I'll give you a heads up on that and the difference between colloquially how we refer to significance versus statistical significance. So just some things to keep an eye out for as we navigate the next couple slides here. All right, so the first project was an analysis that was done. This was a collaborative project between the Appalachian Mountain Club, the AMC, the Observatory, and Plymouth State University. And the result of this analysis was a peer-reviewed published paper back in 2021. And basically what we did was we looked at several climate indicators over this time period you see here, 1935 to 2018, at both Mount Washington Observatory and at Pinkham Notch down in the valley. And basically we looked and analyzed to look for trends over time to see if and how things may be changing at these two different locations and sort of compared what those changes look like. So this table here shows you some of the results of that analysis. And there's a lot of numbers here, so I'm going to break it down for you a little bit more. But basically on that left-hand column there, those are all what we call the climate indicators. Then you have sort of a elaborative definition for those that need some clarification on what those things actually mean. And then you have the results of the trends and rates for Pinkham Notch and the trends and rates for the summit of Mount Washington there. So we'll kind of break this down locationally first, talking first about Pinkham Notch. One thing you'll notice, whether it's spring, summer, fall, or winter, breaking it down seasonally, we're seeing a warming trend across all of those seasons at Pinkham Notch, and those are all statistically significant changes we're seeing over time. One thing you'll notice that might stand out to you, especially guessing there's some winter enthusiasts in the room, the winter temperature in particular and how it's changing more significantly at Pinkham Notch as compared to the other seasons as well, 0.4 degrees Fahrenheit. And also note that these are changes changes per decade. So 0.4 degrees per decade is the rate of change that we're seeing in the winter temperature. And then you have your frost, ice, and thaw days here. So these are days where the temperature fails to or drops below freezing. So we're in general at Pinkham Notch seeing less days where the temperature drops below freezing. And we're seeing more days where the temperature fails to rise above freezing. Now, when we come over to the summit of Mount Washington here, as a comparison, you'll see that most of the indicators still indicate warming trends on top of Mount Washington, but those warming trends are not quite as strong, of a signature as we see at Pinkham Notch down in the valley. And you'll also notice that summer and winter are not statistically significantly changing over time. We are seeing warming, but it's not determined to be significant. But the shoulder seasons are really where that trend stands out on top of Mount Washington. In both the spring and the fall, you see those warming temperatures, again, per decade over time. So digging in a little bit more on this study, these are some this is annual temperature trends. So this is just taking the mean temperature over the entire year and plotting it out going back to 1935 up to 2018. So that top axis there, that's Pinkham Notch, and your bottom line here, that is your summit. And then we're going over time here. The units are degrees Celsius over there, but I've converted these to degrees Fahrenheit for you all. So basically, long story short, at both locations, we are seeing a warming trend, statistically significant warming trend, over the period of this data set here. So for Pinkham Notch, again, warming faster at about 1/4 degree Fahrenheit per decade, and a little bit slower up on the summit of Mount Washington. And I mentioned before that winter is sort of particular interest, and we are seeing some notable differences in wintertime between the summit of Mount Washington and between the Pinkham Notch data set. And yeah, so more of those changes seem to be occurring at Pinkham Notch. So again, that 0.4 degrees Fahrenheit per decade is that signature we're seeing at Pinkham. And then these graphs on the right here, these are exclusively for Pinkham Notch, and they're exclusively looking at some snow total indicators. So if you look at the top, this is your maximum snowpack depth. So basically, we're measuring snowpack at Pinkham Notch every day during the winter. You pick out the maximum value that's observed over that entire winter, that's your maximum snow depth. And then that number is plotted per season over the course of the data set. So you can see there's a marked decrease in how deep the snow is getting at Pinkham Notch over time. And then the bottom right graph here is just total snow that's fallen at Pinkham Notch. So again, you can see that downward trend over time, indicating that Pinkham in general is just recording less snow on average every winter over time. So when we talk about these sorts of things, it's also good to put them in a little bit of context as well. So again, we're back here to talking about those mean temperature changes. So we're looking over the entire year. And so these are the averages sort of on all the different station locations in those bottom three numbers. And again, these are changes per decade in degrees Fahrenheit. So you can see with respect to, say, Pinkham Notch is a little bit more in line with the changes that we're seeing over the state of New Hampshire over this time period, and the Northeast and contiguous US. Again, there's some differences there, but Pinkham is a little bit more aligned with what we're seeing versus the summit of Mount Washington. Again, that warming is happening a little bit slower up at elevation. There's some theories, or I should say there's some hypotheses as to why this is happening. There are other sort of high altitude elevation stations across the globe that have seen the same thing, a slower warming trend. One of the big sort of hypotheses here as to why this is happening is the fact that Mount Washington and high elevation stations are generally they're generally exposed to what we call the free atmosphere more often. The free atmosphere is basically just the elevation above which the land no longer has an effect on the air above it. And so Mount Washington is generally speaking in that free atmosphere. So the theory or the hypothesis there is that in the free atmosphere, you're a little bit more insulated from climate change as opposed to elevations a little bit closer to the ground. But again, this study just looked at what's happening and what the data is showing. Didn't really get into more detail as far as why it's happening. So we'll move on to the second project here very briefly. So this is what we call the White Mountains Almanac Project, and this research is just about complete. So we're now entering the phase where we're putting together a finished product that's going to be published and released to the public, hopefully this fall. This was another collaborative project between AMC, Mount Washington Observatory, in addition to Hubbard Brook, and then we used data sets from a lot of different locations across the White Mountains, the USGS, National Weather Service. There was a lot of data that was crunched. This was all mostly done by one intern over a period of about 5 or 6 months, which was very impressive work that was done. And basically what he did, again, is he broke things down by month and kind of teased out different climate indicators and tracked how they changed over time based on location. So for instance, he looked at February thaw events. How many times in February are we seeing temperatures rise above freezing? Spoiler alert, they are increasing. March winter recreation days. So we came up with sort of indicators for what makes a good day to recreate outside in the month of March. We don't want it to be too cold, we want a nice snowpack, we don't want it to be too windy, and again we tracked those indicators over time, and again we found those March winter recreation days are sort of decreasing over time in general. We also did some phenology work, not my area of expertise, but we did do some phenology work and looked at how alpine plant season is changing over time. And then we looked at things like thunderstorm trends, and we are seeing more thunderstorms above tree line, which could be of particular interest if you're a hiker and you're interested in, say, not getting struck by lightning while you're out for a hike on a summer day. So again, this is all meant to be have some utility to it, to folks who have some sort of a vested interest in the backcountry in the White Mountains. This is also meant to be sort of the first version of this, so we intend to keep at it, to keep updating this almanac over time, maybe including different parameters. Obviously, continuing to do data analyses, we're getting new data every day, of course. So we're, again, there's going to be a version 2, version 3, hopefully version however many we need to do over time. All right, so now kind of into the back half of things here. I just spent probably about 15 minutes communicating science. At least I hope I did. Now I'm sure you got everything, you retained everything, and you would have done things exactly the way I just did. Probably not. That's okay. In general, weather and climate and science is incredibly difficult to communicate for a number of different reasons. And so weather and climate is not immune to this. And so these are just some of the challenges that we face when we communicate weather and climate. I'm going to go through each of them very briefly and talk about how that relates to the film you're about to see, and I'll kind of give you some things to look out for as far as, hey, maybe that's a good idea when we talk about communicating science, communicating urgency. Maybe some things are not such a good idea. So I'll give you some things to look out for there. One disclaimer that I will mention, elephant in the room, obviously things like weather and climate have been heavily politicized. This analysis here is not meant to be partisan or political in any way. This is just meant to talk about the challenges we face as science communicators. But I think I would be remiss if I didn't acknowledge the fact that obviously politics plays a role in all of this. All right, so we'll start first with what I like to call the branding problem. Specifically when we talk about a phenomenon like climate change, the question may arise, what is it even called? When this phenomenon we first started noticing this phenomenon, we kind of started by calling it global warming. But there was some immediate challenges there with calling this global warming. One is, are temperatures increasing everywhere on the globe? Well, no. Overall, on average, they are, but some places are not warming. Some places are actually cooling. So immediately, intuitively, this creates a little bit of dissonance for folks. And then the other fair question is warming a bad thing? I know I like the warm weather. I know many people wouldn't mind having a few warmer days a year. Sounds benign enough. But of course, if you know about climate change and you know the downstream effects, we know a little bit better than that. But still, for those that don't necessarily know much about how the systems all work together, calling it global warming can be a little misleading. So then we moved on over time, and we started sort of morphing into climate change, calling it just climate change. And by we, I kind of mean the scientific community. Obviously, these things kind of, take a life of their own, if you will. But there's some challenges in calling it climate change. Is change inherently a bad thing? Again, it depends on the context, right? And does calling it climate change, does this imply that action is needed? I don't know. Depends. So then we kind of changed gears again, and more recently we've heard more phrases like climate emergency, climate crisis. So these obviously instill more of a sense of action and urgency being needed here. But the fair question is, if it's an emergency, how come things seem normal to me? Now, of course, they don't seem normal for everybody. You can ask the folks in Los Angeles. Things don't seem normal to them right now. You can ask the folks in Asheville, North Carolina, after the wake of the hurricane last fall, obviously. But for a lot of us, it doesn't seem like the world is burning down around us necessarily. So again, it can, you start to create this bit of a challenge with communication of what is the right way to act. And then also you could take it to the other degree and say, if it's an emergency, is it too late to take action then? Does it cripple people out of taking action because it seems like it's too late? So there's no right answer to any of these, and different ones apply in different contexts. I'm just sort of highlighting the challenges inherent with communicating something like climate change. And then you can just zoom out to the graphics. This was just a quick Google search I did. And you can see, based on the words, based on the graphics, based on the colors, a lot of different things can be implied from these as far as levels of urgency, levels of emergency, whether or not we can take action, whether or not we should take action, and when, how we should feel about it, what our response should be. So again, these all convey very different things, but they're all referring to generally the same phenomenon. Then we move on to what we call spatial and temporal dissonance. So the human brain is not really wired to take action against a large, looming threat that's advancing on us very, very slowly. We have evolved to respond to what's right in front of us here and now. So biologically, it's just a really difficult thing for us to wrap our heads around and how we should respond. As opposed to, say, a comet that's heading to Earth, which is very tangible, very acute, very immediate. We have to do something about this, right? Climate change is a little bit more nuanced than that. Climate change seems like it's a problem of the future. It's something that's going to happen in the future. For most of us, hopefully it won't affect us too much in the next 30, 40 years, but not necessarily for everybody. It's going to be, there's some inequity there. The initial impacts are being felt initially in more remote locations, the poles, the Arctic, the vast oceans, places where people don't go and they can't necessarily see the effects that are very, very real and present that are happening right now. And of course, these changes are occurring slowly. They're occurring gradually. Again, like I said, we're not wired for that long-term 30, 40, 50-year impending doom. We're not wired to respond to that. Even the numbers I was talking about in that first study, we're talking about tenths of degrees. Doesn't sound like all that much, but of course it is. Climatologically, it's incredibly significant to see those changes over time. And climate in general, if you take the change out of it, climate in general is just complex in and of itself. That's why climatology is its own branch of science. There's inputs, there's outputs, there's different feedback loops. It's a delicate balance between all of these different things that make up our global climate system. So if you don't understand how it all works, what to look for, how sensitive different inputs and outputs and feedback loops are to different stressors, what tipping points, what triggers are the most impactful. How would you know what to look out for? How would you know when to ring the bell to say we've reached a point of no return with respect to this tipping point versus this tipping point? It's incredibly difficult. And then in communication, obviously communication is all about the words, right? And so even using different terms in different ways creates some confusion. I'm going to give you a couple examples of this. One being the term positive feedback. Sounds good, right? And colloquially, this is probably a definition we can more or less agree on: encouragement or praise that reinforces good performance in the workplace or elsewise. Sure. But scientifically, this has a very specific definition: a process where a change in a system causes effects that amplify that change. It's unbiased. It's not necessarily thought to be good or bad. As an example, as temperatures are warming in the Arctic, it melts more sea ice. Sea ice is white and reflects sunlight, so as you melt more ice, you lose some of that reflectivity. That radiation gets absorbed. Things warm, which melts more sea ice, and the cycle continues. That's a positive feedback loop. So again, not necessarily what you would expect based on how it's used day to day. Risk is another term. This is probably a definition we can all agree on: the chance that something bad might happen. As opposed to, in scientific terms, it's the likelihood that an adverse outcome multiplied, it's just outcome multiplied by impact. And then this one is definitely one that I know is a particular challenge in the scientific versus the just community in general. The word theory is generally thought to mean, I even misused it before if you were catching me, a guess or an idea about how something might work. We generally think of theory as a guess or a hypothesis. Whereas in science, it's actually a body of knowledge. It's backed up by experiment, observation, over time, that explains a natural phenomenon of some kind. So, sort of a misconception that theories become laws, and that's sort of the progression, but really, a law is just explains what's happening, and the theory explains why that thing is happening, which is why the why is more complicated, which is why it takes so much more time. And then these are some additional terms that have a slightly different meaning depending on whether you're talking about them in terms of scientific terms or you're talking about that just in everyday conversation. So again, this adds to the confusion and the challenge. There's pervasive logical fallacies when we talk about climate change or weather in general. You probably heard some of these before. If we reduce or regulate carbon emissions, we sacrifice economic growth. The Earth's climate has always changed, so the current warming is natural. It can't be that bad. This winter it was colder in my town than normal, so where's the global warming? That's a good one. And then if we go back now, the Earth will be uninhabitable in 50 years. So again, these all may have sound like they have a seed of truth to them, but the devil's sort of in the details. So obviously with the first one, this is a bit of a false dichotomy. Economic growth and mitigating carbon emissions are not necessarily a choice. There are ways where you can address both at the same time. The naturalistic fallacy for this next one, just because something is natural doesn't mean it's good, right? I think you all can think of some examples of things that occur naturally that are not good for us. You could think of things like toxic mushrooms, poisonous snakes. Those are natural, right? They're not good for us. Data cherry picking. So obviously when we look at one location in one place in one point of time, you can find anything. You can find any data point you want to find. The key is with something like global warming, with climate change, you're looking over the long-term trends over many different places over a very long time and doing analysis. And the last one is an example of the slippery slope fallacy. Most climate models don't think that even if climate change is unmitigated, that we're going to turn into the planet Venus. So the Earth is not going to be uninhabitable in 50 years if we don't do anything about climate change. But the seed of truth to that is that life could change dramatically. So it's still going to be habitable, but life could change dramatically if we don't take any steps to mitigate climate change. And there could be some locations that on Earth that may be slightly or almost uninhabitable for humans or other species as well. So wrapping up here, so tone and framing is a challenge that meteorologists are no stranger to as far as how we talk about these things. The worst weather gets the most clicks. That's just the reality. A lot of climate change messaging is grounded more in fear. Is that fear unfounded? It's not unfounded, based on what climate models are predicting. However, scaring people into meaningful action, cognitive psychology has shown is just not an effective strategy. And neither is shame as well. You feel shamed, your defensive mechanisms immediately go up, and it kind of paralyzes you or actually works against the goal you're trying to accomplish. Many messengers are operating on an informational deficit model. That's just sort of the assumption that, well, there's not enough information out there, so if everyone just had all the facts, that will sort of illuminate them as to what can be done and how and why. Most experts now agree that is not the big challenge here. Maybe for some it is, but really it's how the message is being conveyed. And there's just, in general, a dissonance between the larger overall problem that seems larger than life and insurmountable versus tangible actions that we can take to address aspects of that challenge on a local level. So it begs the question, what can we do? How can we do it better? And these are just some suggestions that I'm going to put up here. Not all of them will work. A lot of these are already being done. But these are just some things to think about, and also some things to think about in the future, but also some things to think about as we roll the film here, as far as can you spot any of these at work, or can you spot the antithesis of these at work in the film. We can do more local research to analyze local effects. That's sort of where the observatory's mission in all this lies, in looking at what's happening in the White Mountains, what's happening on Mount Washington, and how is that going to affect us locally. Maybe exchange fear for a little bit of hope in the messaging. Like I mentioned before, that fear is not necessarily unfounded, but people tend to respond a little bit better to messages of hope. We can do something about this. There are ways to mitigate climate change that aren't going to paralyze the economy. And we can connect the dots to what matters most for the average person. So making climate change real for people in such a way that talks a little bit about, hey, if we address this sort of energy issue over here, it could mean more efficient heating. It could mean lowering your energy bill in the future. It could mean more sustainable food sources, and maybe those food sources are a little bit more affordable. So connecting it, ways to mitigate climate change to what people care about day to day could be really key in getting the message across. We should lead with areas of more certainty, but also acknowledge the uncertainty as scientists in the science and the potential and the uncertainty in the potential impacts. Because science isn't just a body of knowledge that just stays static. It's a process. We learn things over time. We learn more things. We model, we correct, we move forward. It's a messy, iterative process. And so acknowledging that, I think, is really key when it comes to something as complex as climate change. We can communicate the data through storytelling. People love human stories. And we can tell stories of hope, possibility, and agency. We can use our cutting-edge technology to make a real change. Not just talking about feedback loops, negative emissions, and tipping points, all of those are important too. but I think the ratio there is even more important. And like I said, there's folks that are already doing this. So let's platform those experts whose messaging is accurate, is totally appropriate, based on the moment, based on the circumstance, based on the audience. And of course, we don't want to sacrifice the urgency in all of this, because it is an urgent situation overall. But we want that to be conveyed, but we want it to be conveyed in a way that's not going to paralyze folks out of action. So that's about all I have when it comes to communicating weather and climate change. There is going to be a little bit of time at the end of the film for some additional questions. But again, I would sort of prompt you to, as you're watching the film, to keep an eye out for some of the things I mentioned as far as ways of communicating climate. And again, the film is meant to be an allegory for a lot of different things, including climate change. So you can also keep in mind the differences between a clear and present danger, like a comet heading towards Earth, versus something a little bit more less tangible than climate change.
All right, everybody. Thank you, Mike, so much for coming to talk to us about that. We're going to have a couple of minutes here where you guys can grab some concessions if you haven't already, and then the movie's going to start in just a minute.